Okay, we're going to be looking at some problems from page 548 from chapter 10, talking about the large sample hypothesis test for a population proportion. First thing I want to do is to just emphasize what we are talking about a significance level and a p-value. So if we have a sampling distribution of my sample proportion here, these are the different possible values of p-hat. And of course it's centered along our population parameter, which I'm just going to denote as a p. It's giving me some different p-values and some different significance levels. Now your significance level is basically your total area in your rejection region. So a significance level of 0.05, if it's a two-tailed test, would mean that these two pieces here have a total area of 0.05. The significance level is the willingness I am to make a type 1 error. In other words, the willingness I am to reject my null hypothesis if it just so happens to be one of those strange samples that throw me in the end of the distribution. So that is going to be how I get an alpha. Now your p-value is going to be basically the probability of having a sample that's further out than the one we have. So if I came along and I got a sample that was here, basically I would say, well, anything here or beyond, and anything here and beyond, since it would be just as extreme to be in a two-tailed test to be that far away on the upper side of the distribution as it would to be this far away on the lower side of the distribution, that's where I would get my p-value. It would be the total area of those two pieces put together. So you can see visually that anytime your p-value is larger than your alpha value, you're going to fail to reject the null hypothesis, because that p-value of 0.08 was more likely to occur than my alpha level. In other words, if I were to reject my null hypothesis at that particular value, I would be accepting basically an 8.5% chance of making a type 1 error, and I was only willing to make a type 1 error if alpha was 0.05. Now on the skipping down a couple, later in this problem I have a p-value of 0.84. So let me draw what this one would look like. So in this case, my p-value is 0.084. I'll go ahead and draw it like this. So that means the total area, I would have something over here and something over here. So the total area on those two pieces would be 0.084. And in this particular case, the alpha is 0.1. So that means my alpha would be, my critical values would be right there, so that I would have about 10% of my distribution there. So you can see in this case, since your entire probability region in your p-value, that entire thing falls within my rejection region, the region that represents the most extreme 10% of the values, I would reject my null hypothesis. So in a nutshell, anytime that your p-value is less than your alpha value, that is when you're going to be rejecting your null hypothesis. When p-value is less than alpha, you're going to reject your null hypothesis, and that means you're going to say that you have statistically significant results. Anytime your p-value is less than alpha, you reject your null hypothesis, saying you have statistically significant results. Now, for 26, it's actually giving you z-scores and wanting you to find a p-value for the z-score. I'm going to reach for the calculator to help with this. So what I do is since it's a z-score, I need to know the probability of having a value above that z-score. So I'm going to do normal CDF, and my lower value in this case is 1.40. And then this alternate hypothesis, since it's a greater than, I'm going to go above 1.40 all the way to there, something just very big, press enter, and that gives me this number here. My 0.08 is my p-value. Graphically, if you were trying to sketch what that would look like, that would have looked like something like this, with this being your distribution, and there is your z-score cutting off right there of 1.4, and it's cutting off this p-value of basically 0.08 something of the distribution. Now, depending on your choice of alpha, if alpha would have been 0.5, I would have said, well, the p-value is higher than alpha. I have failed to reject the null hypothesis. On the other hand, if my alpha was 0.1, I would say my p-value is less than alpha, so I would reject my null hypothesis and find statistically significant results. Now, all of these are basically a one-sided test. Just to show you the difference, this would be how I would calculate a p-value when my alternate hypothesis is a greater than. If my alternate hypothesis was a less than, what I would do is I would basically go in the other direction. So instead of shading over in that direction, if it was a less than, I would shade this way, which would give me a huge p-value, which I would very obviously fail to reject my null hypothesis. And if it was a not equal to, in that case, on the not equal to, we would say it doesn't just matter if I'm 1.4 extreme this way, it also matters if I'm equally extreme or negative 1.4 that way. So if it's a not equal to, it's basically going to double your p-value. So instead of being just the 0.08, it would be about 0.16. But for this particular problem, they were all greater than, so you can just start at your z-score and go to infinity. Last thing I'm going to touch on is on problem number 27. It's asking if it's appropriate to use my large sample test for a population proportion. Well, basically what I need to know is my sampling distribution of p-hat going to be approximately normally distributed? Because remember, just like when we were doing confidence intervals, it's important to know that this sampling distribution of p-hat is approximately normal. When I'm doing hypothesis testing, it's also appropriate to know it's approximately normal, because if I did have a skewed distribution, getting a z-score, I cannot trust this z-score at all to find the probability. With a distribution that's not approximately normal, that z-score is not going to tell me the probability of being past that point or having a result at least that extreme, so my p-values will not be accurate. So that's why I need to check for normality when I'm hypothesis testing. And the test is the same as it was when you were doing confidence interval. Both n times p and n times 1 minus p need to be bigger than 10. So for the first case, I have a population of, a probability of 0.2, so 0.2 times a sample size of 25. So in that case, that's just going to give me a value of 5. So since this condition fails, it does not matter that the other condition will pass. Since this condition did not work, my answer would be no. It is not appropriate. So if you end up both, just like with the confidence intervals, both of your conditions have to pass for you to say that the sampling distribution is normally distributed and to go forward with your hypothesis test.